So let me rewrite that because I'm going to run it soon. Oh, by the way, I hope you guys don't mind that I'm using half a page on these, not only because I'm using the calculator, but that lag was just driving me absolutely crazy. Let me show you another way to do this one. If I take f of x, where am I? F of x equals x squared over 3 plus x. Now watch this. I can just as easily rewrite this. I'm going to do a couple moves at once here. I'm going to take the x squared out. So this x squared thing, it scares me. There's too much going on. I'm going to factor out a 3 because I need that 1 there if I'm going to do the geometric thing. And then this is going to, times, and I'm going to be left with 1 over, remember this? 1 minus negative x thirds. They are identical algebraically. Now I can just simply deal with this series. Now a equals 1, r equals negative x thirds, correct? So this is equal to x squared thirds times the sum, as n goes from 0 to infinity, of 1 times negative x thirds to the n, which I could rewrite as x squared thirds times the sum, and goes from 0 to infinity, of negative 1/3 to the n times x to the n. When I distribute this guy through, because I need that, remember the power series has all the x terms inside of it. When I distribute this guy through, what I get is the sum, as n goes from 0 to infinity, of, now again, I end up with negative 1 to the n times 1/3 to the n plus 1. And I can't put those together because when I plug in 1, I'm going to get a different value for the 1/3 than I will for the negative 1 as far as how it works out. So I've got to split them apart. This is times x to the n plus 2. Now here's the coolest part. Watch this. Remember, this equals this. So f of 2, let's say, which we know f of 2, if I just plug it in, what do I get? I get 4/5. 4/5 had better be equal to, exactly equal to, the sum, as n goes from 0 to infinity, of negative 1 to the n times 1/3 to the n plus 1 times, you ready? Put a 2 in there. 2 to the n plus 2. That's another crazy way to write 4/5. Now, why would you want to? I don't know. But it's another way. So you got that to work with. All right? That'll keep you off the streets at night, as it were. Fantastic way to deal with series and functions. So what we're doing is we're creating a marriage. Now, the thing to bear in mind for this chapter is you only have one tool, and that tool is the geometric. Now, in the next little section, I'm going to get crazy with it. All right? I'll show you that in just a sec. I'll meet you back. All right, now check this out. What I'm about to do is going to blow your mind. Remember when we took f of x equal 1 over 1 plus x squared, and we proved that that equaled the series from n equals 0 to infinity of negative 1 to the n times x to n. Okay? Now, remember, don't I know that the integral of dx over 1 plus x squared is equal to the inverse tan of x plus c, right? So let's see if I can marry a derivative of a function that I know. If I want to turn this function into a series itself, and I know that its derivative is this. Well, watch. I mean, if I take the integral of dx over 1 plus x squared, isn't that exactly the same thing as taking the integral of the sum, as n goes from 0 to infinity, of negative 1 to the n times x to the 2n dx? Do you agree with that? So this guy right here becomes the integrand because they are identical functions. There's no difference. Now, you may say, Ripley, you're blowing my mind here. I'm really not. Think about it. Just answer one question for me. What is the integral of a sum? It's the sum of the integral, right? The integral of a sum is the sum of the integral. So really what that tells me is I can turn this into the sum as n goes from 0 to infinity. I can pull the addition part out times times the integral of negative 1 to the n times x to the 2n dx, right? Integral of a sum of the integral. Just pull the sum out and deal with this, right? The integral of a sum is the sum of the integral. So watch what happens here. Now this is where it gets absolutely crazy. This becomes the sum as n goes from 0 to infinity of, well, negative 1 to the n, notice dx. So whatever isn't an x is just a constant, and that includes n's, and that always freaks students out. All right, so don't freak out. All right, here we go. I'm going to go negative 1 to the n, that's a constant, times, what's the antiderivative of x to the 2n? Well, it's just x to the blah thingy. And how do I do that? I go x to the 2n plus 1 divided by 2n plus 1. And then let's not forget our c. Now, how am I going to deal with that c? What's going to happen with that c? Well, watch. There's such a cool little trick. If I think about this, now you may say, well, where's the c go? Does it go inside? Does it go outside? Who cares? It's a c. I can put it inside of all the terms, and when I add a whole bunch of c's together, guess what I get? I get a c. So I might as well represent it as one big fat c on the outside of the sum so I can deal with it. Okay? Now, check this out. I know that this equals the inverse tan of x. Correct? That's really what I'm looking for. All right? That's what I'm trying to figure out. You see what's going on here? I know, because if I take the derivative of this side, I get 1 over 1 plus x squared, which I know if I take the derivative of this side, I should get this guy right here, because I just took its antiderivative. The question is how do you solve for c? The answer to that's real simple. Simply take a value where you know the answer to both the inverse tan of that value and if I plug it in to this series. So how about let's let x equal 0 and see what happens. Let's see if we can solve for c. Doesn't this imply that the sum as n goes from 0 to infinity of negative 1 to the n times 0 to the 2n plus 1 over 2n plus 1 plus c equals, well, what's the inverse tan of 0? See, the tangent of what angle? Oh, that's 0 as well. Hey, guess what this whole term goes to? 0. So this implies that 0 plus c equals 0, which implies c equals 0. Now, what does this tell us? It tells me that because of the integral slash derivative relationship between the inverse tan and 1 over 1 plus x squared, it tells me that I can rewrite inverse tan of x as the sum as n goes from 0 to infinity of negative 1 to the n times x to the 2n plus 1 over 2n plus 1. Now, there's another really cool thing, and it's that whether you take an integral of or a derivative of a series, which is mind-blowing to think about, I know, especially right now, but with a little practice you'll do fine. The radius of convergence is r. Okay, it's going to be preserved, in other words. You're going to preserve the radius of convergence, which means that this is true for, remember before when we did this guy? This is going to be true when x is between negative 1 and 1. And the only thing that can throw this off is, because notice we're not talking about a truly geometric series here, we might want to check our endpoints. Do that real quick. Check our endpoints. Throw 1 and negative 1 in there and see what happens. See if any voodoo occurs and see if those somehow make it in. Because notice this series, I got to make sure that I emphasize this. Notice I raised my voice. That implies emphasis. This guy right here is not a geometric series in the same sense that this guy and this guy were. This guy and this guy were. These two are married through the geometric series. These two are not. All right, we took an integral. Clearly, inverse tan, there's no way if I were to say, okay, f of x equals inverse tan of x. If I ask you to turn that into one of these guys, you mutiny. I'd have a full-scale mutiny on my hands. All right? Let's look at another one here in just a sec. Actually, I'm recording in the middle of fourth period, or where are we? Yeah, fourth period. So I'll come back and record the second half of this a little bit later. See you in a bit.